Welcome everyone to lecture 2A. We're going to start talking a little bit deeper into our intermolecular forces and focus this particular lecture on hydrogen bonding. So we looked at some dipole forces, and there are certain molecules that have a very special type of dipole interaction, and this particular interaction is called hydrogen bonding. So let's just real quick compare two molecules, acetone and water. So if we look at acetone and water, if we were to measure the dipole, we would see that the value of the dipole for acetone is larger than H2O. So acetone has a larger delta plus, a larger delta minus, and so it will form a stronger attraction between the delta minus and the delta plus of adjacent molecules. If we look at the sizes of the molecules, we can see that acetone is clearly a larger molecule. It has a higher molar mass. It has a significant larger number of electrons, and so it will have greater London dispersion forces as well. So we can throw that into the mix, and we can see that the attraction between two acetone molecules should be greater than that of two water molecules. However, if we start to look at boiling points, we see that acetone boils at 56 degrees Celsius and water boils at 100 degrees Celsius. And what this means is that the intermolecular forces between two water molecules is actually greater than the intermolecular forces between two acetone molecules. So those two things don't really jive together. The various intermolecular forces that come into play, your dipole and your London forces for acetone are both stronger, and yet water has a higher boiling point. So let's kind of see what's going on here. Well, let's just look at acetone just real quick so we can see what's happening. And if we look at the structural formula here, our acetone molecule is actually bent as opposed to what we see in the structural formula here. It doesn't really change much, but we can see that we would have a delta minus on the oxygen here, a delta plus on the carbon here, and we get that molecular attraction there. We see that exact same thing here in the space filling model where those two attractions come into play as well. So what makes water so special? Well, it has to do with the fact that you have a highly electronegative atom, oxygen, attached to a hydrogen. Now, remember when we were talking about bonding, we've got two electrons being shared between these two atoms here or these two atoms here. And when that more electronegative atom, oxygen, has the electron, if you want to think of it that way in terms of time, well, there's no other electrons around the hydrogen there, and so we call it a naked proton, essentially. So, and when we have that naked proton, when there's no other electron, there's no electrons around that hydrogen, then the nucleus, which is just nothing more than a proton, is completely exposed to any charges that are around it, and so it actually develops a very strong positive partial charge, and this is because there's no shielding around that hydrogen nucleus. And so what we end up getting here is you have this strong delta plus here in coordination with the delta minus there, and this is called a hydrogen bond, where you have a hydrogen attached to a very strongly electronegative atom bonding with the strongly electronegative atom of another molecule. And the only time that this occurs is when that hydrogen in the molecule is bonded to either a fluorine, an oxygen, or a nitrogen. Those are our three most electronegative atoms in the periodic table, and those are the only three atoms, when a hydrogen is bonded to them, that we can create a situation where hydrogen bonds are allowed to form. It's not enough just to have oxygen, fluorine, or nitrogen in the molecule. A hydrogen must be attached to those atoms in order for hydrogen bonds to be formed. If we look at the differences between hydrogen bond and a normal dipole interaction, your hydrogen bond is going to be somewhere in the range, generally 2 to 4 times stronger than a regular dipole interaction. That's pretty significant. The hydrogen bonds is the primary force holding the double helix strands together in our DNA, and we know that those are pretty strong. The other type of intermolecular force we have isn't really an intermolecular force, but it does involve at least a molecule, but it involves a molecule that has a dipole, so a polar molecule, and an ion. And so this occurs when an ionic substance is dissolved in a polar solvent. It can be just something as simple as salt water, so sodium chloride, an ionic substance being dissolved in water, a very polar solvent. So aqueous solutions become the most common examples. When you have an ionic substance being dissolved in a liquid, those ions separate into their cations and anions. They carry a full positive and a full negative charge, or even more, depending on which ion you have. And the charges that are on those ions can interact with the permanent dipole on the polar molecule. And these do create a fairly strong attraction. So we can look at examples of that here. We get these ion-dipole forces. So here's the example of sodium chloride being dissolved in water. And so here's a chloride ion here, the Cl minus from sodium chloride. And that is a full minus charge. And of course, a full minus charge is going to interact with other positives around it. And there's a lot of water molecules in an aqueous solution. So you're going to have that delta plus of the hydrogen atoms on water. They are going to be attracted to that Cl minus, and it does form a little cage around that chloride ion. And we say that ion is now hydrated. We see the same thing here with our sodium ion, except now we've got a full positive charge on the cation, and so that's going to interact with the negative portion of the dipole of water. And so we still have an ion-dipole interaction here. So if we can summarize this, all of our different intermolecular forces, we have London dispersion that are due to this random distribution of electrons within a molecule, creating a very tiny delta plus and a very tiny delta minus. All molecules and atoms have London dispersion forces. We see that they're generally fairly weak, but as we talked about in the previous lecture, they can develop very strong interactions if there are enough electrons. We can move up to our polar molecules that create dipole-dipole interactions, so they permanent dipole due to differences in electronegativity. So we have a delta minus on like an oxygen here and a delta plus on a carbon here, and those delta minus and delta pluses can interact and attract the two molecules to each other. Hydrogen bonding, just a type of dipole-dipole interaction, but very specific conditions have to exist. You have to have a hydrogen atom bonded to a fluorine, an oxygen, or a nitrogen in order for hydrogen bonding to set up. And then we have ion-dipole interactions, and because we are now dealing with a full positive or a full negative along with a dipole, those attractions are actually very strong because of that full positive or full negative charge on the cation or anion, and we can see here the strength over here is quite a bit stronger.